Quotients. So quotient means division, obviously. If we have two radicals with the same index, you'll notice that this has an n and this has an n. These have to have the same index for this quotient rule to work. Then if you have a fraction, these are the same thing. What this means really is that you could reduce the fraction and then take those roots, or you can take the roots individually. It doesn't matter, but that root applies to both the top and the bottom. So sometimes fractions get confusing in a radical, but you can just think of it as the root of the numerator and the root of the denominator. And whichever way is easier to do it, you can do it that way first, meaning reduce it first or take the root first. It doesn't matter. Let's do this first example right here. The cubed root of 2/12. So in this case, I would probably reduce first. So I'm just going to reduce that fraction. Both the top and the bottom are divisible by 2. So that is going to reduce to the cubed root of 1/6. So now I'm going to think of that as the cubed root of 1 over the cubed root of 6. 1 always has a root. No matter what the index is, the root is 1. Okay? So positive 1, no matter what the index is, this guy is going to equal 1. 6, however, does not have a cubed root. It doesn't have a square root. It is just 2 times 3, okay? And so to get rid of a root, you really have to multiply it by how many times it is a root, if that makes sense. So I only have 1 6 in there. To pull a 6 out of that root, I would have to have 2 more 6s, if that makes sense, okay? So I actually have to multiply it by the cubed root, this is new, of 2 6s. Because in order to pull that out, I have to have 3 6s because my index is 3, okay? And right now I only have 1. Why would I do this? Well, it is not proper math to leave a radical in the denominator, okay? So just like you would not give me the answer, you would not say, okay, my final answer looks like this. Something in you should say, that's probably not the final answer, because that can be simplified, right? And the same goes for roots. You do not leave a root in the radical. It's not simplified form. It is not considered simplified form. We are accustomed to something like this. Everyone knows how to get that out, hopefully from Pythagorean theorem and stuff like that. We've used radicals many times. We're just accustomed to doing something like this to get a radical out of the denominator. The thing is, we're used to using square roots. Why did I multiply it once? Because that gave me 2 of what was inside of my radical. My index was 2. So I could pull out a 2 because I now had 2 of them, okay? But here, I have a cubed root. So I can't just multiply this by 1 cubed root of 6. That only gives me 2. 2 of them will not take it out of the radical because my index is 3. I have to group it in 3s. So I have 1 6 here, and I had to multiply by 2 more of them inside the same radical. And just like any fraction, if I multiply the bottom times that cubed root of 6 squared, I have to multiply the top by the cubed root of 6 squared. Now on the top, I really just have 1 times this root. So I just have the cubed root of 36 up there. That's all I have. But on the bottom, I have created 1, 2, 3 6s, and I just have a 6. All right? You cannot reduce that 36 and the 6. You can only reduce outside to outside. This 36 is inside the root. This 6 is outside of the root. So I cannot reduce this any further. And if I were to factor tree my 36, then you're going to see that you do not have any groups of 3 that can come out of it. I didn't have anything that could simplify to begin with. I still don't have anything that can simplify. So this is as simple as it gets. This is my answer. When you have an imaginary root, you want to go ahead and pull that imaginary out first. In fact, typically, when you have a radical in the denominator, you want to simplify it as much as possible before you what's called rationalize. Rationalize is what I just did in number 1. Before you get the radical out of the denominator, go ahead and simplify it as much as it will simplify. So in this case, I have a -3. That will actually simplify because I can pull an I out right now. Okay? And so I am going to take an I out of my root here. And I'm going to have 18 over 3I square root of 3. And I actually am going to try to get that I out of the denominator as well. I'm also going to try to simplify my whole problem first. So before I do anything else, I'm going to say, can anything simplify at this point? Well, yes. 18 and 3 simplify, right? And so I want to simplify that before I start moving stuff around. So I'm going to divide both by 3, and I'm going to get 6 over I square root of 3. Okay? And so when I do this, I actually am going to multiply the top and the bottom by I square root of 3, because I really don't want an I in the denominator either. Typically, your i's are only in the numerator. They're not in the denominator position. So we want to get the radical and the I out of there. So we're going to multiply the top and the bottom by I square root of 3. If I have an I here and an I here, it's going to cancel itself out, I squared. I only had to do it once because it was an index of 2. So I have 2 of my 3's. I'm good to go. It will come out. So now I'm going to have in the numerator position, I am going to have 6I square root of 3. And in the denominator, I'm going to have I times I, which is I squared. And then square root of 3 times square root of 3, all that does is it gets rid of my root. Looks like that. Okay? Now here's the thing. I don't want to reduce these. I want to simplify my I squared another way. What can I replace my I squared with? Yeah, so that's 3 times negative 1 in the denominator. So this is 6I square root of 3 over negative 3. And I can reduce it. 6 and negative 3 reduce to what?
2.
Yeah, so negative 2I square root of 3 is my answer. So I am going to actually rewrite this one to look like a fraction, all right? I'm going to say 2 plus 6I over 3I, all right? Now here's the thing. I don't have to get the 3 out of the denominator because it's not a radical. I don't have to do that at all. But I do need to get the I out of the denominator. So I'm going to multiply the top and the bottom by I. If I multiply the top by I do have to distribute it. So I'm going to distribute it through. 2 times I is 2I. 6I times I is 6I squared. And on the bottom, I have 3I times I have 3I squared. All right. And now I'm going to simplify this. I'm actually going to do this by splitting it up. All right. So I am going to simplify this piece. I'm going to say 2I over 3I squared plus 6I squared over 3I squared. All right. And remember, we don't want to cross out i's. If we have an I squared, we want to simplify it using our negative. And so I am going to rewrite this one as 2I over negative 3. So 2I over negative 3. And I am going to simplify the next one as negative 6 over negative 3. All right. So negative 6 over negative 3. Now let's look at this little piece right here. When I have an I involved, just write it as a fraction. Negative 6 over negative 3 is positive 2. So I actually have negative 2/3 I plus 2. Complex numbers actually have a standard form. If you remember complex numbers, A plus BI is your standard form. So you'll notice in the book they switched it around. You always write your real part first. Well, the 2 is my real number here. And the negative 2/3 I is my imaginary part here. So that's actually the format that you would see it in standard form. It's like writing, you would never write like 3x plus 2x squared plus 1. right? Standard form says I would write that 2x squared plus 3x plus 1. That's how imaginary numbers, complex numbers are. Complex numbers, you put the real part first, the imaginary part second. So that's why it's been rewritten that way. Remember, fractional exponents are actually radicals. So just like you wouldn't have a radical in the denominator, very often they don't want you to leave fractional exponents in the denominator. This is not always true. Sometimes they'll let you do it. But if it tells you to simplify this, it's intentionally telling you to get that fractional exponent out of the denominator, okay? So when you think of a fraction, the way you get a fractional exponent out of a denominator is to get it to 1, okay? So this one's a little bit different than what we've been doing. With this, I have to consciously think about, well, what is going to make a 2/5 1 if I am multiplying? What happens when I multiply like bases? Well, if I were to say x squared times x cubed, what happens? That becomes 2 plus 3, right? 5. So I need to multiply this base 3 by something that when I add the exponents, it becomes 1. What do I add to 2/5 to make it 1? 3/5. So that's what I'm going to multiply the top and bottom by. 3 to the 3/5. Top and bottom by 3 to the 3/5. All right. So on top, I have 5 times 3 to the 3/5. On bottom, I have 3 to the first power, which is just 3. And that's actually how they want you to leave that. I know that's weird, but that's how they want you to leave it. All right. When they say simplify a fractional exponent in the denominator, that's what they want you to do. Because you can't really do anything else. I mean, you could rewrite it if they want it in radical form, 5th root of 27, 3 cubed. I mean, potentially you could rewrite it as a radical. You need to recognize those are the same answer. But simplifying a rational exponent in the denominator is just getting it to 1. Getting it to 1. Or at least to a whole number that you can square it or cube it or whatever. All right? Notice that instead of just having a radical in the denominator, we have a radical plus something. This is a binomial. Think of it as two terms added together. So I cannot simply just multiply by square root of 3, because if I multiply this base by the square root of 3, it'll get rid of this guy right here, but then I'll have 2 times the square root of 3, which does not solve my problem. So I'm going to use the concept of conjugates here, okay? Conjugate. The conjugate that we have seen in the past is something like this, a plus b, a minus b. Those are conjugates of each other. And so when I have something in the denominator that I want to get rid of, I multiply by its conjugate when it is a binomial like this. So I'm actually going to take this problem here, and I am going to multiply the top and the bottom by the conjugate of the denominator. So my conjugate's going to be the same two terms. I do not change the first sign at all. If this is a positive square root of 3, I leave it a positive square root of 3. To get a conjugate, I change the center sign. This was a plus. I'm going to change this to a minus. And I'm going to multiply the top and the bottom by that conjugate. Here's the thing. If you'll recall, when I multiply these conjugates, I end up getting the first one squared minus the second one squared. That's how this will always work. So how does this help me? Well, on the top, I am going to have to FOIL my original numerator and that conjugate. But on the bottom, I'm going to end up the first one squared. What happens when I square a square root? I just get what's inside. So I square this first guy. Square root of 3 squared is just 3 minus the second one squared. 2 squared is 4. Okay? So I end up with this little shortcut here. On the top, I need to FOIL. So I have 8 times the square root of 3. 8 times negative 2. Negative square root of 3 times positive square root of 3. And negative square root of 3 times negative 2. All right. On the bottom, I have 3 minus 4. That's just negative 1. All right. So I'm going to simplify my top. Simplify my top. 8 square root of 3 and 2 square root of 3 are like terms. That is 10 square root of 3. Negative 16 and negative 3 are like terms as well. And that's all over a negative 1. So I actually end up just dividing each piece by negative 1. So positive 10 square root of 3 becomes negative. Negative 19 becomes positive. And they actually flip-flop these just because it looked prettier to do it this way. But that's all I'm doing there. So I'm using the idea of conjugates to get rid of my radical now. And you actually do the same thing for imaginary numbers. We're getting ready to do an imaginary number as well. So when you have a radical in the denominator that has a plus or minus, you're going to use this concept of conjugates. Let's look at this last example, example 5. I'm going to rewrite this like a fraction. I have 2 plus I on the top, 3 minus I on the bottom. Remember I said you don't want to leave an imaginary in the denominator either. But once again, if I just multiply by I, I'm still going to have an I in the bottom because of that 3. So I have to use that same concept. The conjugate then is 3 plus I. And I'm going to multiply the top and the bottom by the conjugate of the bottom. Okay, so I'm using the conjugate of the denominator. This is going to create the same thing, the a squared plus minus b squared. So when I have something like this, I'm always going to end up with the first one squared minus the second one squared. That's what's happening on the bottom here. The first one squared minus the second one squared. That's what I have down there. On the top, I am going to have to FOIL these. All right, and so on the top, 2 times 3 is 6. 2 times I times 3, and I times I. On the bottom, 3 squared is 9 minus I squared is negative 1. All right, and so I can also replace this guy with a negative 1. And I have some like terms here. I have 6 minus 1 gives me 5. 2i plus 3i gives me 5i. On the bottom, I have 9 minus a negative 1. That is 10. And then I'm going to simplify this the same way I did the other one. I'm going to divide them out. So I'm going to put the 5 over the 10 plus the 5i over the 10. And then you can see that those will reduce. 5/10, that is 1/2. 5/10 I is 1/2 I. And that is my answer there.